So, hello everyone. My name is Sayyad, and I'm studying computer science at BITS Pilani campus. So, my project is oil spill drift simulation, which is basically a sequel to his project. His was detection, mine is simulation. Yeah, I ended up using the same image as a coincidentally. Yeah, so I'll just quickly go over the same thing which you went over. There are many impacts like the marine life, like in large oil spills, like for entire decades, there's no wildlife down to the ocean floor. You won't find anything of that. Even mangroves, if like it goes to a coastline, now the mangroves die out. And yeah, fisheries, of course, like they also in oil spill affected areas, no wildlife survives. So people who are dependent on fishing, uh, like their livelihood will be lost. And yeah, in the last like 50 years, like 1,800 medium to large oil spills have occurred, and several more small scale oil spills have occurred. So that's a huge economic loss as well because we are losing our natural resources in this manner because there's no way to actually uh, collect the spilled oil. What they basically do is they skim the oil and it's basically unusable. It becomes, it changes chemically, sort of. So, if we can't stop the oil spill, we should at least be able to help in its cleanup. So, we can help with that by oil spill modeling. So, there's been years and years of research in this field. There are like multiple equations for each of the processes. There are multiple processes that occur to the oil after the oil spill. So the simulation is basically like the first few days after you detect a spill. So the oil particles are modeled according to a numerical model which follows the physics equations, and then you can see which area will be affected. So that helps the cleanup crew. And you can also see like if it will reach the coastline or not, so you can secure your coastline as well. So basically, there's two kinds of fluid mechanics: Lagrangian and Eulerian. Eulerian is when you treat a fluid as a bulk and you apply equations to the bulk of the mass. But oil doesn't actually behave like a bulk; it actually splits up into multiple parts. It behaves more like particles. So Lagrangian fluid mechanics is when you treat fluid like a bunch of particles and you apply equations to each individual particles. So, like years of research has shown that this is the most accurate way of modeling oil. So the inputs that we require is basically the location of the oil spill, the type of oil spilled, so that we can know the properties, density, etc., and the amount of oil spilled. With that and years of equation in our hand, it's pretty easy to do it. Yeah, but there's a bunch of things which happen to the oil. There's basically spreading and advection. So when it's spilled, there's a bunch of it in a water column, like a few feet below the surface. But after like 10-20 days, it becomes like a millimeter thick slip. And yeah, it gets like some of it evaporates, some of it like sinks to the ground and mixes with the soil, some of it gets dispersed. So it's a very complicated process. So I went through a lot of the research papers and I identified three main processes behind it. Uh, so these are just like the differential equations. They are not actually the ones that you can use in a numerical model. So this one is the most important one. This is like the wind and the water, they push oil on top of it, and the majority of the velocity is caused by this. And advection diffusion, this basically changes the amount of oil, like how amount and density, like some properties of it. At the end, you get like something called an oil budget, which tells you how much evaporated, how much like sunk down, how much is still in the water column, how much is in the slip. And this is called, the third one is the vertical mixing. So if you don't implement vertical mixing, then your model will falsely do a lot of spreading. So that we think that. And yeah, I tried to model it, and I have to be honest, I couldn't do the oil. I couldn't model the oil within process. I misjudged how long it would take to implement me, because there are like 8 different equations, and there are like the vary in sensitivity, which ones matter. Mostly evaporation and emulsification are important, but the rest, so I couldn't figure out how to assign weights to these equations. So I left them for now. So yeah, in my review, I found out what was the best approach. So when you get the droplets, like when you make the particles in which you would apply physics. So like older models, they use like fixed classes. Like every droplet will have the same size, but that's not how Excel oil behaves. So you need to have a range of oil droplet diameters. So you have to calculate that using another equation. And then we don't have an equation for turbulence. So what we do is we apply random ticks to like all particles, and that is how we model turbulence. So the basic random walk approach, what happens is like there's diffusivity, which is basically how turbulent a region is. So in this, when oil goes to low diffusivity zone, it will get stuck there, because there not be enough force or kick to move it out of there. But in reality, oil will never get stuck on a water surface; it will always be moving. So there's a Visser corrected random walk scheme which like handles that. And then surface spreading, yeah, if you don't include 3D vertical transport, then you will overestimate spreading. That's why I included that. And yeah, Eulerian is, it's only accurate when it's near the spill source. After that, it's not accurate at all. So that's why I went with the Lagrangian approach. So the beneficiaries, mostly the Coast Guard, because they'll be able to simulate in case of earthquakes where they most of their manpower will be needed, and the regulation agencies, they can do risk assessments like this coastline or these mangroves. What is the risk that if an oil spill occurs here? What is the probability that oil will end up here? And yeah, port authorities and Ministry of Defense as well, they can also benefit from good oil spill model. So yeah, so this was something which gave me a lot of trouble, the entrainment rate coefficient. It's sort of not very accurate, the equation for it. The value was going very high, and it was not modeling it realistically, so I had to introduce a cap to the entrainment rate. So there's more research needs to be done on this subject, but maybe without research as well, you could find a solution. But that was the best I could do. Yeah, oil withering processes, we need to implement that. I couldn't do it, but if you want to know the oil weathering, this is important. And yeah, the database, sometimes you might not get some certain properties of oil from the radios. Yeah, I didn't talk about databases. Basically, I'm pulling water velocity from CMEMS, Copernicus, and I'm pulling wind velocities from ERA 5, and I'm pulling the oil properties from NOAA's radios database. So this is like the long-term plan, like building the model, which I sort of did. And these two are remaining, like testing it against the other oil spill models, and then testing them against actual like uh, documented oil spills. And yeah, picking it up with like his projects with. And yeah, that's it. So now I will show you the results. I generated this like this morning. So these are the inputs I gave. Uh, yeah, I used mass instead of volume because like the density might change, but it doesn't matter. You can use volume as well. I can change that. So 50,000 kgs of oil was spilled in this location of the type Bonnie, right? It's a lightweight oil. At this, like this, I chose like a random in the somewhere in the ocean I wanted. So it's like it's near Africa. So yeah, the model how it works is there's a time step involved. So it will apply the equations to our particles and it will find out the trajectory at every time step. Like it will find out how when it where it will be after 1 minute. Then after 1 minute, it will take fresh data of where it's gone, like the water element was there, and it will apply again equation, and then it will find out where it will be the next minute. Because like computers, they have to be discrete; they can't do continuous. And I simulated for 12 hours because so it doesn't take too long to generate. So this is the droplet size simulation, which not too important, but it was one of the things that you need. And like this is uh, the 3D water column. This you can see like how this is at the end of the 12 hours. Like most of the oil is here, but some of it is below the surface. This is just a simulation. This might or might not occur. It's like stochastic because we used random picks to generate it. If we ran it again, we'll get something slightly different. I mean, even I don't understand what this is. I generated. You get a net CDF file as an output. It's a trajectory file, and I don't know how to open it. You can just visualize it using different tools. Uh, and I converted it to CSV and I opened it in QGIS. So at the beginning, it's like this, all of them bunched together. And then, yeah, I added a video of it like, spreading. It doesn't spread a lot because like 12 hours is not enough time for it to actually spread. If you can see, it had started here and it only spread till here. If I had run it for longer, then it might have gone like here, and it would have spread a lot. Uh, so that's it for my project. And if you have any questions.